Click. We are now recording. Okay, good afternoon and good morning, everyone, wherever you might be. It is my pleasure to introduce my new postdoc at IMPAN, XIAO Han. He did his PhD with Gianni Landi at CISA, and he will tell us about Hopf-Galois extensions and the gauge group of Galois objects. It's all yours. Take it away. Go ahead. XIAO, we cannot hear you. Hello? XIAO, we cannot hear you.
Now you cannot hear me?
Now we can hear you, yeah, but only now.
Okay.
So please start over.
okay, I start again. No problem. Okay, welcome to my talk. And today I will give a talk on Hopf-Galois extension and the gauge group of Galois objects. And there are two sections in this talk. In the first section, I will talk about Hopf-Galois extension and a special example of non-commutative Hopf fibration. And in the second section, I will talk about the gauge group of Galois objects. Okay, so now let's start with some fundamental concepts. First, recall that a bialgebra is an algebra H together with two algebra maps, delta H from H to H tensor H, which is called core product, and also another algebra map, epsilon H from H to C, which is called core unit, such that it satisfies the equation 1.1, which is so-called a core associativity condition and core unit condition. And moreover, if there is a linear map S from H to H, such that satisfies 1.2, which means the convolution product of S and the identity H is equal to the epsilon H times 1H. Then we call this bialgebra a Hopf algebra. And given two Hopf algebras, H and G, Hopf algebra morphismus from H to G is an algebra map from H to G. And moreover, this phi should be also a core algebra map in the sense of 1.3. Okay, so for any Hopf algebra, a H core module algebra is again an algebra with a linear map delta A from A to A tensor H, such that it satisfies the core associativities and the core unit, and moreover, delta A should be an algebra homomorphism. And for this core module algebra A, we can define the subalgebra of core invariant to be the collection in subalgebra in A such that delta of B is equal to B tensor 1H. And we will always use the Samley-Sweeter notation to represent the image of the core product and the core actions. And now, because we have 1.5 hours today, I can write them the core associativities and the core units on the whiteboard, so everyone can see my whiteboard now, right?
Yep.
Okay, so then if I write them in Sweeter notation, we can write delta A is equal H is equal to H1 tensor H2, and the core associativity means H11 tensor H12 tensor H2 is equal to H1 tensor H21 tensor H22. Okay, and the core unit condition means H1 times epsilon H2 is equal to epsilon H 1H, and this is also equal to epsilon H1 and H2, and this is just the condition for the core product. And to be a Hopf algebra, we also need to require the core product delta to be a core algebra map, which means delta of GH which is by definition equal to GH1 tensor GH2, which is equal to G1 H1 tensor G2 H2. And for the antipode, okay, I think I need to change another. Okay, I don't know, but then I will show you how the antipode works in this case. So this is only that under this condition, this is only it's just by algebra, but for Hopf algebra, we need to have the antipode. Sorry. Sorry. Okay.
So far, this is all algebra. I mean,
yes. Yeah, they are just algebra.
There's nothing in here. So far, there's nothing in here about C-star algebras or Bionic algebras. These are just algebras.
Yeah, just really algebra without any norm. Yes, exactly.
There's no norm.
No norm, it's just the algebra.
Yeah, it's just pure algebra. Okay.
Yes, exactly. And okay, until now we just talked about by algebra, but being a Hopf algebra, we also need to introduce the antipode, which is a linear map from H to H, such that S of H1 times H2 is equal to epsilon H times 1H, and this is also equal to H1 times S of H2. Okay, so the Hopf algebra can be viewed as a quantization of a group, and the antipode here plays the role of the inverse operation on the group structure, and the core product plays the role of the multiplication of the group, and the core unit plays the role of the unit. Okay, and this is now I will show you also the core product on the core action on the core module. So the core action on a core module, which is given on the which is a map delta from an algebra to a tensor H, and this is a right H core module. And by Sweden notation, we can write delta of A is equal to A0 tensor A1. And usually they have the bracket over 0 and 1, but here I just make it simple. And this map is the co-associativity, means A0 tensor A01 tensor A1 equal to A0 tensor A11 tensor A12. We usually reorder the index by 1, 2, and 3 instead of 0, 1, 1, and 1, 2, because we can always do this. And moreover, this delta map is a algebra map, which means AB0 tensor AB1 is equal to A1, no, A0, B0 tensor A1, B1. And for any AB belongs to the core module algebra. Any question?
The line before the last line, is it A10, A11?
Yeah, sorry, yeah, A00, A01, the A1, and here is A0, A11, A12.
That's correct.
Yeah, it's correct, right? Something wrong here. Okay, so now it's just the sumless with the notation on the Hopf algebra, and also is a core module algebra. And now let me share back my screen to a slide. Okay. So this is just some record of sumless with notation, and now we can after we have this core module algebra A and the corresponding Hopf algebra, we can then define the canonical map, and that is a linear map from the balanced tensor product over B of a tensor A to a tensor H. And if we write them down explicitly, it's a map which map A prime tensor A to A prime A0 tensor A1. And the canonical map of then we call this extension to be a Hopf-Galois extension if this canonical map is bijective. So we usually also call the Hopf-Galois extension to be a quantization of principal bundle. In a sense, on the right-hand side, we can see there is a principal bundle of P over M with a group structure, with a structure group G, and M is invariant under this G action on P. And on the right-hand side, we have Hopf-Galois extension, where the total space have a co-action by H, where B is also the subalgebra of co-invariance, which can play the role of the function on M, and A can be viewed as a function on the P. But Hopf-Galois extension is non-commutative, since both A and B can be non-commutative, and also the Hopf algebra can be non-commutative. And in the following, we always assume for any Hopf-Galois extension, the algebra A is a faithful flat left B module. And also the requirement of this canonical map being bijective is also claim the same story of the definition on the principal bundle, since there is also a canonical map on the principal bundle, which is a map from P times G to P times P. That is a map from P comma G to P comma PG. And if any G space for which the canonical map is bijective, then this G space is a principal bundle. This is another definition instead of to define the freeness and the transitivity of the G action. We have if the canonical map is bijective, then this is a well-defined principal bundle. Okay, now I will give a special example of Hopf-Galois extension. And especially this is a special example of a Hopf fibration of S7 sphere over S4 sphere. And first, I will define the algebra on the total space. So here AR is a star algebra generated by two sets of Hermitian elements, x1 lambda and x2 alpha, with lambda. The index lambda vary from 1 to n1 and alpha from 1 to n2. And they satisfy the commutation relation in 1.6, that is x commute with themselves, and x1 commute with themselves, and x2 commute with themselves too. But x1 and x2 are commute up to a R matrix. And this quadratic complex algebra has the following properties. And first, AR is graded algebra, which means AR can be written as a direct sum of its graded subvector space. And second, this algebra is connected, which means the zero grade subvector space is equal to the complex number. And third, the first grade subvector space is a linear span of x1 mu and x2 lambda. And at last, the second grade of this vector space is equal to the linear span of x1 lambda, x1 mu with lambda smaller than mu, and x2 alpha, x2 beta, and also with a mixture term x1 lambda and x2 alpha. And if everything commutative, I mean also x1 and x2 commute each other, then there is a classical solution on the R matrix. That is, the R matrix can be given by the product of two delta function, delta tensor. And in this case, AR0 is nothing but the coordinate algebra over the product Rn1 times Rn1. And assume that the mixture basis x1 lambda, x2 alpha are linearly independent, then we need to have some restriction on R given by 1.7. And now we reorder the index by a single A. And in this case, x lambda is equal to x1 lambda and x alpha plus n1 is equal to alpha x2 alpha. And then we can write the commutation relation 1.6 in a single relation 1.8, but this commutation relation are replaced by this matrix R. And this is a matrix element of endomorphism of AR1 tensor AR1. Okay, and so we can see this 1.7 can be translated into the relation on mathematical R, that is 1.9, R0 equal to 1 tensor 1. And next, we want to impose the matrix satisfy the Young-Bax equation 1.10. And this Young-Bax equation then can break into a series of conditions from the beginning in 1.6, the commutation relation of x1 and x2. And finally, we also need to require both a quadratic element x1 square and x2 square belong to the center of AR. And finally, we can obtain the some symmetric condition on R by exchange on index. For example, in 1.11, we can see by exchange on index, we can see R lambda beta alpha mu is equal to R mu alpha beta lambda, and similar for some the complex conjugate and R inverse, and by exchange on index. Okay, so by exchange the index of mu and lambda, mu and beta, we can define a new endomorphism R hat, which is endomorphism of Rn1 tensor Rn1, Rn2, and then this matrix can have representation by several matrices AR, BR, and CA, DA, where AR are real symmetric N1 matrix, and BR are real symmetric N2 matrix, and CA are antisymmetric N1 matrix, and DA are real antisymmetric N2 matrix, and all of them are taken to be linearly independent. And moreover, under the restriction of the Young-Bax equation and all the conditions above, we can conclude the matrix AR commute with themselves, and matrix of CA commute with themselves, and AR and CA commute. And similar for BD and BD, they all commute with each other. And they also have the normalization condition that is coming from 1.9, that is the sum of AR, AS, tensor BR, BS plus CA, CB, tensor DA, DB is equal to the tensor product of two identity matrices. This is just the translation of the involutive condition on our matrix. Okay. So now I will give a more explicit example on the R matrix. But first, let's consider the quaternion Q with coefficients from x1, x0, x1, x2, x3 with a basis ek, where ek are a quaternionic basis, and then we can define a left and right representation of the quaternion by relation 1.17. That is jk plus is the left representation of ek by multiplication on the left, and the jk minus is a representation of ek by multiplication on the left, and jk and ja plus and minus can be given explicitly by 1.18, and we can see j plus and j minus commute with each other since quaternions are associative algebra, and we can also see J plus and J plus satisfy the similar commutation relation as the unit quaternion, and similar for the right representation of quaternions. Okay. And now using this matrix, we can get a special commutation relation R matrix. And in this case, we have R matrix with 3 parameter U0, U1, and U2, and compare with what with our matrix given in 1.20, we can see in this case we have A equal to identity matrix and B equal to U0 identity matrix, and C is equal to G1 plus, and D is equal to U1 G1 plus U2 G2 plus, and where we can see both A and B are symmetric 4x4 matrix, and C and D are also anti-symmetric 4x4 matrix, and they also satisfy the commutation relation we gave in 1.13 and 1.40. And moreover,
you are giving an example of a Hopf-Galois extension?
Yes, I'm now giving an example of Hopf-Galois extension, and now I'm first introduce the total space algebra A, and this total space algebra A is a non-commutative, and
What is your Hopf algebra?
what is Hopf algebra is a SU2, A of SU2. I mean the function on SU2.
Classical SU2.
Yeah. This is a classical.
That's going to be the Hopf algebra.
Yes, that is going to be Hopf algebra. I mean the group algebra have its corresponding core product with a commutative, and this is corresponding. This is a Hopf algebra, and I will give it later.
The Hopf algebra is functions on SU2.
Yes.
Yeah. Polynomial functions, regular functions.
Yeah, the polynomial function. Yes.
Polynomial functions are regular. Okay, on SU2 is a compact Lie group, right?
Mm-hmm.
Yes.
It's a three-sphere. I mean, topologically, it's a three-sphere.
Yes. Yeah, topologically right? Three-sphere, and also it's a unit quaternion.
It's all yes. Okay. Yeah. It's unit quater. Oh, so unit quaternions. That's your Hopf algebra. Unit
yes,
quaternion.
Exactly.
Okay, unit quaternion is your Hopf algebra, and now you are going to construct what algebras on which your Hopf algebra is acting.
Yes. Now I'm constructing the total space algebra, where this Hopf algebra have a coaction.
You want a coaction on certain algebras, right?
Yeah, exactly. But first, I will.
Okay, what are those algebras on which this will act?
Yeah, the algebra is given later, which is A of S7R, but I will talk in a few minutes.
Okay.
Okay. So now we can see this combination relation R have a parameter U0, U1, and U2, and they have the restriction that U0 square plus U1 square plus U2 is equal to 1, and this restriction comes from the relation 1.15. And we can also see that this R matrix is parameterized by the two-dimensional sphere. Mm-hmm. Okay, so now it's time to define the total space algebra. As I mentioned above, we know x1 square and x2 square belong to the center, so is their norm. So we can define the non-commutative S7 sphere by the quotient of the A of R8 over the ideal generated by the norm equal to 1. So this is the total space. This is 7 sphere, but non-commutative, and they have a commutation relation given by the R matrix. And now we consider two quaternion, x1 and x2, with coefficient x1 mu and x2 lambda, with their commutation relation given before. And then we can define the vector value of the function on S7R, that is phi equal to x2 and x1 with its norm equal to 1. Okay, thus we can get a projection which is a Barthes of phi, and we can also write it in terms of x and x1 and x2. That is, for example, the first integer is x2 and x2 star, and we can check that this matrix is a projection since p is equal to p star equal to p square, and if we define another coordinate function y to be y0 e0 plus yk ek, and y4 equal to the difference between x2 square and x1 square, and y equal to 2 times x2 x1 star, then we can write p in terms of y and y4. Since p is a projection, then we can check y mu generate a star algebra of S4 sphere in the sense of 1.24. That means the norm square of y is equal to 1. More explicitly, we have the sum of y mu star, y mu plus y4 square equal to 1, and also y mu times y mu star plus y4 square equal to 1.
Shao, please wait, I'm confused. What are these E0, EK? Can you remind me? These are coordinate functions on where? On your S7?
Yes. So here, x are the coordinate function on S7, and here y are the coordinate function on S4. I mean y0, yk, and y4.
But you already mean quantum or?
Yeah, this is already quantum because x1 and x2 are non-commutative. I mean, they are not commute with each other. So that's why we have this A of S7 R, and they are generated by X1 and X2. And since they are not commutative, then this is a quantum S7 sphere. And similarly, we can see there is also the non-commutative relation between Y's.
Okay, so these E's are simply give you basis of the quaternions, right?
Yes, the E are just the quaternion basis. Exactly.
Okay, thank you.
So we can see because of 1.24, we can see this the Y generated the S4 sphere. Okay, and now we have the algebra inclusion from S4R into S7R, and this is the SU2 bundle, and with the action in the following. So we know that SU2 is isomorphic to the unit quaternion, and this act on S7 just by multiplication on the right by on both X2 and X1. And clearly this projection and also the algebra of A of S4R are invariant under this action. Okay, so in the language of Hopf-Galois extension, we can see in this case, the corresponding Hopf algebra is just the functions on SU2, and this have a coaction on S74 with co-invariant subalgebra on A of S4R in the following instance. And recall that this Hopf algebra A of SU2 is a unit complex star algebra generated by omega 1 bar, and omega 2 bar, subject to the relation that omega 1 bar plus omega 2 bar equal to 1. And they have also the core product, and we write them in a compact way. And to be more precisely, we can see delta of omega 1 is equal to omega 1 tensor omega 1 minus omega 2 tensor omega 2 bar. And similar to the omega 2 example, delta of omega 2 is equal to omega 1 tensor omega 2 plus omega 2 tensor omega 1 bar. Any question?
No, it's just standard matrix multiplication.
Okay, it's just a standard matrix multiplication, but in this way, I just write them together.
Yeah.
Okay. And for the core units, we have epsilon of omega 1 is equal to epsilon of omega 1 bar equal to 1, and epsilon of omega 2 equal to epsilon of omega 2 bar equal to 0. And the antipole S of omega 1 equal to omega 1 bar, and S of omega 2 equal to minus omega 2. Now we want to define a new coordinate, that one equal to that x10 plus x11 e1, and that's 2 equal to x12 plus x13 e1, and similar for z3 and z4. And with the help of this new coordinate, we can then define the coaction from A of S7 to A of S7 tensor the Hopf algebra. This is given explicitly by 1.26. For example, delta of that one is equal to that 1 tensor omega 1 plus minus that 2 tensor omega 2 bar. Okay. And we can also see this algebra is can be generated by alpha, beta, and gamma in terms of that one. That's, for example, alpha is equal to 2 times that 1, that 3 bar plus that 2, that 4 bar. And we can also see A of S4R is co-invariant subalgebra under this coaction. And we can also, until now, we have two, for the algebra A of S4R, we have two set of generators. One set is Y and Y4. Another set is alpha, beta, and gamma. And alpha, beta, and gamma can relate to Y and Y4 in the relation 1.28. So both of them are coordinates, are generators of A of S4, and they are all co-invariant under the coaction. Okay, so to show this is a Hopf-Galois extension, we also need to show that corresponding canonical map is bijective. Since in this case the Hopf algebra A of SU2 is called semi-simple, then we only need to show the canonical map is surjective, and moreover, since the canonical map is left alinear, is sufficient to show each generator on the Hopf algebra have a pre-image, by the under the canonical map. For example, chi of that one bar tensor that one plus that two tensor that two bar plus also for that three and that four is equal to one tensor omega one. So each generator omega one, omega two, omega one bar, omega one two bar have the pre-image. So we can see this canonical map is surjective, and also we know this is bijective since the Hopf algebra is called semi-simple.
Yeah, let me weigh in for a second because that's an important point. This theorem of Schneider is really beautiful and profound and difficult, and this is just a very special case. He has it for simply faithfully flat cases, and faithful flatness here is guaranteed by cosine simplicity of H, but it's a very special case.
Yes. So more question here? Okay.
I think the argument is clear. I mean, bijectivity is tantamount to surjectivity, and because of left A S7R linearity, all you need to do is to show that one tensor every generator of H is in the image, and that's what you just did. So
yeah, exactly. That
so
is
you prove that your action of SU2 on this S7R is actually free. That's what you just proved.
Yes, exactly. And then I also proved this canonical map is surjective, and also since the Hopf algebra is called semi-simple, then we can induce this canonical map is also bijective.
Yeah. Just a silly question. When you look at your S7R, you do have some natural C-star completion. Am I right?
I think so. There should have some C-star completion, but in this case, we didn't think about the C-star condition yet. But I think there should be some C-star completion over this algebra. But we didn't work on this direction.
Because there are some funny deformations. I don't know, Jordan type that have only unbounded representations or whatever, and then you cannot have a completion. But I believe this is not the case here. But it would be good to know.
Okay, probably we can work later to see how is the C-star completion is under this algebra.
And is the theta deformation an example of your R deformation?
Yeah, the total space is R deformation, and the base space we can see later is a theta deformation, but I will talk it in a few minutes.
Okay. Take your time.
Okay. So now I will start the commutation relation for the base space as S4, and so we can see the coordinate function on base space Y have a relation with Y star. That is, Y star is equal to lambda Y for lambda be a symmetric unitary matrix given by 1.29 and 1.30. And after calculating the eigenvalue of this 2x2 matrix, we can diagonalize this matrix into with the diagonal element 1 and e to the I theta, where e to the I theta is equal to the difference of the two eigenvalue, and then we can see this as for a sphere is going to be the theta deformation as one have introduced by Alan Kang and Gianni Landi in 2001. And now we have the Hopf vibration where the total space is S7, which is deformed by a S2 sphere, and the base space S4 is deformed by a S1 sphere. And this is a special example of the Hopf-Galois extension. Okay, so now I will go back to the generic theorem on the translation map of the Hopf-Galois extension. So recall that there is a translation map also on the principal bundle. That is a map measure the difference of the print on the same fiber. So dually, we have for a given Hopf-Galois extension B into A, there is since the canonical map is left alinear, then its inverse is determined by the restriction of chi-inverse on one tensor H, which is called the translation map. And the translation map have several properties, and we can write them into the composition of tau and the identity tensor epsilon A is equal to delta composed with tau tensor identities, which when we write it explicitly by 1.33. And also similarly, we have another proposition given by 1.34. Okay, so compare with the translation map on the G principal bundle, that is a map which map MP times P over M. Here is a pullback of the projection map on M to G, which measure the difference of the two different points on the same fiber to G. And 1.33 and 1.34 means the translation map T of P comma QG equal to T of PQ times G, and T of PG comma Q is equal to T G inverse and T of PQ. And moreover, there are also some other properties which were introduced by Thomas Straczynski and Wiesbauer. That is from 1.35 to 1.39. For example, 1.35 read in the classical case is T of P comma PQ PG equal to G, and 1.36 means T of PP is just the one because there are no difference between P and P, and 1.38 means T of PQ times T of QW is equal to P T of P comma W.
And this is a very important equality. You'll need it for your Ehresmann groupoid.
Yes, this is very, all of these properties are very important whenever you're doing the calculations on the X1 by algebra exactly. And finally,
and you see, all this stuff makes sense because your action is free. I mean, T wouldn't be well defined if it were not for the fact that G acts freely on M. And this is reflected on the Hopf-Galois side by the fact that tau is defined as a restricted inverse.
Yes. Yes, exactly. I mean, the bijectivities also imply the freeness of the action on the total space. Okay, and finally, there is a correspondence between 1.39 and the translation map, which read P times T of PQ equal to Q. Okay, so there are just some facts on the translation map of the classical principal bundle, and here we have the translation, and they are all very important when we define the Ehresmann-Schaumann group by algebra we will introduce later. Okay, so here I will skip the proof. So if we have time, we can go back. So now I will give the introduction of gate transformation of a Hopf-Galois extension. And first recall that a gate transformation on the classical principal bundle is a map F from P to P, which is G equivariance, which means F of PG is equal to FP times G. Moreover, we call this gate transformation to be vertical if F preserves the fiber. So dually on the Hopf-Galois extension, the gauge group consists of the algebra map from A to A, which are also read H co-module linear and also unital, such that the restriction on B belong to the automorphism on B. And the sub-collection of the gauge group means the subset on the restriction that F restrict on B is equal to identity on B. Okay.
Sorry, Shao, don't you need to assume that your map is bijective?
No, this one is not necessarily bijective. It's just.
No, I mean F, lowercase f.
You mean this F?
Lowercase.
Lowercase.
Yeah, not capital F, lowercase f.
Oh, you mean this F? Okay.
Yeah.
This F. I think. I think it could be automatically bijective, right?
Well, that's what I was thinking. But what if I map? So you cannot shrink the fiber. That's obvious. But what can stop you from mapping all fibers into one fiber?
Okay.
Right? Imagine that we have some stupid bundle that just has only 2 fibers, trivial bundle.
Yeah.
And then let's map all these 2 fibers into 1 fiber. Then you will have equivariance and not injectivity, not surjectivity.
Oh, okay, I see. So
I think you have to assume
some correspondence. I think we need to have some correspondence of the F restriction on the algebra to be automorphism. That we need to have this F composed with a projection to be some diffeomorphism on M. And this makes sure we cannot map all the.
Oh yes, of course. If you make it, of course, if you make another thing that, for instance, the induced map on the base space is identity, then that's okay.
Yeah. I think
because you see the equivariance condition.
No, Piotr.
You use a map on the base.
Piotr, map on the base, but not identity on the base yet.
Sure. Well, when you have classification of principal bundles, you actually want identity. But of course, it need not be identity. Yeah. But if you say that on the base you are bijective, then of course you are bijective on P. Yes, Ludwig. Yes.
Yes, I mean also this map. What we means here, the map is a bundle map, between 2 different principal bundles. This induced automatically. We cannot map the different fiber into a single one because this is the bundle map.
Yeah, but you didn't write it. You see.
Okay. So
okay. It's a classical principle, but it's a map. You just said it's a map. You didn't say it's a bundle map.
Oh, sure. I should say this is the bundle map. Yeah. Sorry for the comment. Yeah, this is the bundle map. Yeah, I should mention that.
Okay. Then it's okay, because when you say that it commutes with pi, the projection, that's it. It's automatically bijective. And then you can, in the non-commutative algebraic setting, talk about automorphisms. Okay.
Yeah, exactly. This should be a bundle map. Sorry for this. I think
1-0 for us.
Yes. This is a bundle map. That's why we have the restriction of F on B. It belongs to automorphism.
Oh, yes.
B.
Yes.
Agreed. And then we have the vertical one is a restriction on B is equal to identity on B. Yes.
Yep.
Thanks for the comments.
Yep.
Okay. And
now we're good.
Then we have the proposition that if B, the subalgebra of co-invariants, belong to the center of A, and then we can see the collection of the gauge transformation from a group with a group multiplication given by the composition of map, and the identity the unit of this group is just the identity map from A to A. And the inverse of this group element F inverse is given by 2.3. And here we need to use a translation map A11 and V12. And one can also check A0 F of A11 belong to B tensor A. Okay. So in particular, the vertical homomorphism, I mean the vertical gauge group also form a subgroup of the gauge group. Okay.
Wait a second. Sorry, Shao. Why do we need this assumption of B being in the center of A just to have a group structure?
Yeah, I mean, since we want to have, so for some detailed computation, whenever we need to require this F inverse to be again an algebra map under this formula 2.3. After some computation, we can see if B is not belong to the center, then we cannot derive F inverse to be an algebra map, and also the composition of 2 different maps, like F comma G is not an algebra map anymore, even if F and G are algebra map. So they always need some commutation relation of B with some other element in A.
Wait. So when you say, could you please go back to this out H of A, the definition? This is automorphism mean what in algebra sense?
Yes, automorphism means. First is the algebra map. So what is said is the algebra homomorphism, which is unitary, and also it is the right H comodule map.
Okay, so all these Fs are algebra homomorphisms, right?
Yeah, all these F are algebra homomorphisms, exactly.
So I don't see how when I have a bijective algebra homomorphism, I can always compose it with another one.
Okay.
And since it's bijective, I can make an inverse, and everything is going to preserve. I don't question the later things, but just
No, this F is not automatically bijective. It's just the algebra homomorphisms. And if B belongs to a center, then it have an inverse. Otherwise,
it's confusing that you call it out, because when you say out, I would think it's an automorphism. Automorphism are just by definition bijective. I mean, come on.
Yeah, sure. Yeah, this probably is not a good notation, but I mean, in the definition itself, it doesn't require F be a bijective map. But if B belongs to a center, then we can always get the inverse F inverse to be the inverse of F for both the left-hand side and right-hand side. And we also need to require this inverse in the relation 1.3 to be the core module map and also be an algebra map.
Okay, so let me see if I got it right now. So we just discussed that if I have a bundle map which is equivariant, then it's automatically bijection. And you are trying to reproduce, or you are simply reproducing this fact in the non-commutative setting, but under the additional assumption that the coaction invariant subalgebra is in the center of the total space algebra. Am I right?
Yeah, exactly.
Okay. So this discussion was good actually before, because it clarifies what you are doing in this proposition.
Yeah, exactly. This is the case. Yes.
Okay.
So,
I'm good.
So far, so clear, right?
Yeah.
Okay, great. So we always need to assume B belongs to a center in order to get this inverse is a algebra map. And now after this gate group of Galois objects, Hopf-Galois extension, I will give introduction of biaggregate and especially the Ekman-Schauenburg biaggregate. So first, the biaggregate can be viewed as a quantum group right, and especially the Ekman-Schauenburg biaggregate can be viewed as a quantum gauge group right, corresponds to a Hopf-Galois extension. But before biaggregate, I will first define the B ring. For any algebra, a B ring is a triple A, mu eta, and where A is a bimodule with together with a bimodule map eta from balanced tensor product A tensor A to A, and eta from B to A, which is also bimodule map, satisfies the associative condition and unit condition in 1.4 and 1.5. So for any algebra map between two algebra B and A, then A can be automatically became a B bimodule induced by phi by multiplication on the right and left and right hand side. And moreover, A is a B ring with a unit to be phi and be the algebra map. Okay, so dually we can also define the core ring for an algebra B. The core ring is consists of triple. C is again the B bimodule, and the delta is a bimodule map from C to the balanced tensor product of C tensor C, and epsilon is again a bimodule map from C to B, satisfy the core associativity and core unit conditions, see that in 1.6. We can see that when we replace B by some fundamental field, for example, a complex number, then a B ring and a B core ring is just a K algebra and a core algebra. Okay. So now after the B ring and B core ring, we can start to define the left biaggregate of one algebra B. So a left biaggregate is first a B tensor B orb ring introduced from an algebra map eta from B tensor B orb to L, such that the restriction of eta on the first factor is the algebra map from B to L, and the restriction of eta on the second factor is the algebra map from B orb to L, and S is called source map, and target, and T is called the target map. And we also need to require they have the commuting range in L, and moreover, L also have a B core ring structure on the same vector space with the three compatibility conditions. First, as a B core ring, the bimodule structure on L can be given by the source and target map by multiplication on the left-hand side of A. And second, the core product is the algebra map from L to a Takeuchi product of L times L, where Takeuchi product is a sub-collection.
What product?
And Takeuchi product.
Takeuchi, you mean?
Takeuchi, sorry.
Takeuchi.
Takeuchi, yes. Takeuchi, the pronunciation is not correct. Sorry. So it's a sub-collection under the restriction of 2.8. And this algebra is was given by multiplication component-wise. And finally, we also have the co-unit, which is a left character on the B ring, which means it satisfies the unitarity conditions, and second, it satisfies the left B linearities, and at last, it need also satisfy the co-associativity condition. So here the reason why we need to co-restrict the core product on the image, which is the subalgebra of the balanced tensor product, is only in this way we can give a well-defined multiplication over the balanced tensor product. Okay, maybe I can, because we have enough time, I can write them again on the whiteboard. So I remove out here. Okay, so here we are. So we have first. Okay, so we have first two elements, C prime over B, and C double prime tensor C triple prime over B, and then they have a multiple. They are both two elements belongs to L tensor L over B, and now we want to calculate C tensor B C prime times C double prime with a red action tensor by C triple prime. Okay, so this is equal to C tensor C prime over B times TB times C double prime tensor C triple prime. Then this by the multiplication factor wise, we can say this is equal to C TB C double prime tensor C prime C triple prime. And so by using the Tarkovsky product, the restriction on Tarkovsky product, we can see this one is equal to C double prime tensor B of C prime S B C triple prime, and this is in term to be C double prime tensor B, and we have B act on C triple prime. So we can see in this case, we have B can move from one side of the tensor product to another set of tensor product. So on one case, we have B act on C double prime, and on another side, we have a B act on the C triple prime. So that's why we need to use the Tarkovsky product instead of just the tensor product. Okay, so now let's go back to the definition. So then this is all the definition of the bialgebroid. Now I will give a special example of bialgebroid, which is so-called the Ekman-Schoenberg bialgebroid. And Ekman-Schoenberg bialgebroid can be viewed as quantization of the classical gauge groupoid. And first, let's recall the classical gauge groupoid corresponds to a principal G bundle of total space P or M. So first consider the diagonal action of G on P times P given by the multiplication on the right-hand side of U and V, and we denote the equivalent class of U comma V being the orbit of UV, and omega being the collection of the orbit. Then omega is called the gauge or Ekman groupoid of a principal bundle with the source and target map given by 2.9. That is the source map sin U comma V being the projection on the second factor, and T of U comma V is the projection on the first factor.
And why like this, not the other way around?
You mean S is equal to projection of U? Yes, I mean, this is, you can also make another way around, but yeah, you can see this is even not due to the case of the solid Untitled Map in what we call the left Eichmann Berger point. So that depends. If we define another way around, then we have an opposite on the corresponding Eichmann Berger point, which I will show later. But I think you can also define S equal to pi of u. This is not a problem. The only thing is to make them compatible with each other.
Sure. I just a quick remark, because I tried to establish what is the dominating terminology, and it's actually hard because Ehresmann himself called his groupoid a structural groupoid of a principal bundle.
Okay.
And some people call it, as you did initially, the gauge groupoid of a principal bundle.
Mm-hmm.
Some other people call it Ehresmann symmetry groupoid. So it's quite a mess. I don't understand why such an important and beautiful and canonically given groupoid has problems with its name. But it does.
Yeah.
I mean, if you type into Google Ehresmann groupoid, it will not spit out anything interesting. After a long search, I found these three names: Ehresmann groupoid, gauge groupoid, and structural groupoid, and Ehresmann symmetry groupoid. It's actually four names.
yeah, that is an interesting story on the names. Yeah, but here, yeah, we usually, I think the gauge groupoid should be the most common name in different article, right?
Mm.
Okay, so as a groupoid, we also need to have the inclusion map from the space of object to the space of morphisms, and this inclusion map is given by 2.10. That is a map from M to U comma U in the equivalent class, where U belongs to the fiber over M in a corresponding principal bundle. And also we need to define the composition of the morphismus space, that U comma V prime times V comma V is only definable whenever V and V prime belong to the same fiber. And the multiplication is given by 2.11, that is U comma V times V prime comma W is equal to U comma WG, where G is the difference of V and V prime on the same fiber. And this G can also be calculated with the help of the classical translation map that we introduced before.
Yeah.
Okay, so one can also choose a representative to make V and V prime be the same. And in this case, the multiplication can be simply written by U comma V times V comma W equal to U comma W. And the inverse is just given by the flip of the order of U and V. That is in 2.12. Okay, so after this classical one, I will talk about the quantum groupoid. This is also so-called Ehresmann-Schonburg-Berger point associated to a Hopf-Galois extension. So assume this Hopf-Galois extension is still feasible flat left bimodule. Then the bimodule C is given by 2.13 with the help of the translation map. And we can see later this is quite abstract compared with the classical definition of the orbits collection. And we can also see this is also equal to the subalgebra of co-invariant under the diagonal coaction. But first, let's define the Eichmann-Berger point as a vector space given by 2.13 with the help of translation map. And the core product is given by 2.14 with the help with the help of the translation map. And this 2.14 is due to the product given by 2.11, since here we need the translation map in calculating the G. And here we also need the translation map in the dual case. And the core unit is given by 2.15. That is just a multiplication of A and A tilde. And this coring is called the Eichmann or gauge coring. So to have a Berger point, we also need to have an algebra structure on a given vector space. And this algebra structure is given by the multiplication factor-wise, where the first factor is just the A and the second factor is opposite algebra A. And unit is just a 1 tensor 1. and the source and target map are given by 2.17. That is the source map send B to a second factor, and the target map send B to a second factor, and the source map send B to a first factor. You can see this relation 2.17 is nothing but due to the relation 2.9. But here we have reversed the case. So here is the source map send this element to the product on the second factor. But here we have S or B put B on the first factor. So this
exactly, this is why I asked this question, because it's, it's more natural to have it like in 217, in my opinion.
Yes, this is not natural, but at the beginning we also have the target and source map in which S of B is equal to 1 tensor B, that is put B on the second factor. But in that case, we need to have the corresponding right by Algebra point. But we found that it's much more easier and convenient to use the left by Algebra point. So that's why we need to exchange the position of the source and the target map, and then we have the corresponding 2.17. But this is not an issue. I mean, it's just a compatible with themselves. It should be okay, but it still is a quantization of the gauge group point and assorted to a principal bundle. And this is the case. I understand why you are asking this question, because we also face this problem. And then we calculate everything and change every T and S in that case in order to get the letter by Algebra point. Okay. And if this corresponding Hopf algebra have an invertible antipole, then we can see the box tensor product of A with A given by the left and the right coaction. That is, it also this box tensor product is the same as bimodule with the C of AH, and this is a sub-vector space with restriction under 2.18. And we can see this relation imply in the classical case that is B, G, Q is equal to P, Q, G inverse, because they are in the same equivalent class. And moreover, we can see the sub-vector space of co-invariant under the diagonal coaction is also equal to the X-man Algebra point. As a Algebra point under condition 2.19, where this 2.19 is nothing but a co-invariant sub-action under the diagonal coaction, because this is a definition. And you can see that this 2.19 is just due to the definition of the X-man group point, the classical X-man group point, since here the omega is just a collection of the orbit, where the orbit is just an equivalent class under the diagonal action. And here we can see the X-man algebra is just a collection of a co-invariant subalgebra of the diagonal coaction. So that's why we call it X-man Schoenberg algebra to be the quantum gauge group point.
Just one quick remark. Can you go back? Yeah. So if you look at the top, yes, if you look at the top of this slide, of course, what you wrote is true, that right coaction is left linear and right coaction is left linear and left coaction is right linear, and it's true even for C-Galois extensions, for coalgebra extensions. But here in the Hopf-Galois setting, they are just bimodule maps over B. I mean, they're both left and right bilinear, because this is a Hopf algebra case.
Yes.
So just a small remark, because the way you put it, it seems like delta A is only left bilinear, and delta A with A on the left is only right bilinear. They're actually both B bilinear. But of course, you highlight it because this is exactly this linearity that you need in order to define things, right? But,
yeah, exactly. So in order to define the box tensor product, we also need to have delta, the right A to be the right bilinear, and the delta A on the left is the right bilinear in order to define the box tensor product. That's true.
Exactly. Yeah, the cotensor product, yes. But and this is the reason why it works for C-Galois extensions when it's really only one side linear.
I beg your pardon, I don't understand, sorry.
This is why all that stuff works also for C-Galois extensions for coalgebral extensions. When coactions are only right coaction is really only left linear, not right linear, and the induced left coaction is only right linear, but not left linear. That's all we need to define this cotensor product.
Yeah, exactly. Yeah. Okay. So now I will give an introduction of bisection on the X-Man diagonal point. But first, let's again recall some concept of the classical case. The bisection of the classical group point is a map sigma from M to omega, such that the composition of sigma with S equal to identities. A composition of sigma and T is equal to the diffeomorphism on the object space, and the collection of the bisection from a group with respect to the multiplication given by 2.20, and the identity bisection is just the inclusion from M to U comma U is the equivalent class, and the inverse is given by 2.21. And here we can see this is well defined since we already know a composition of sigma and T is a diffeomorphism on M. Okay, so now we have also the bisection on the quantum gauge group, right? That is a unital map from the diagonal point to B such that the composition of T with sigma equal to identity on B, and composition of say S and sigma belong to the automorphism on B. And we call this bisection to be vertical if sigma is the left inverse of left inverse of the source map. That is S composed with sigma is equal to the identity on B. And we can see later that the vertical bisection also have some relation with the vertical gauge group, which we will call later. Okay, so again, if under the condition B belongs to the center, we can then get a collection of bisection from a group with a product given by the sense of convolution product of the bisection. And the unit of this group is just a co-unit of the diagonal point since it's a map from L to B. And the inverse can be also given in 2.23 with the help of the translation map. Of course, the subset of the vertical bisection from a subgroup of the bisections. Okay. So now we have introduced two groups. On one hand, we have the gauge group on the Hopf-Galois extension. On the other hand, we have the group of bisection on the corresponding X-Man-Schoenbrück diagonal point, and both of them are grouped under the condition B belongs to a center. So one may ask, so we recall that in the classical group point and the principal bundle, the bisection of gauge group point is one-to-one correspondence with the gauge transformation on the principal bundle. So in the dual case, in the quantum group point,
could you show this fact? Could you show like this calculation on screen of what you just said?
Yeah, I mean here I'm just recalling some classical facts. So there is a classical correspondence between the bisection with the gauge group, and now I'm going to explain how they related in the quantum case. But now I'm just starting now.
Yeah, okay, but I was wondering if you could explain this one-to-one correspondence in the classical case. I of course believe it, but I cannot do this calculation in my memory.
Okay. Yeah. Okay. So probably I share my screen again, and now I don't know how to remove all of them.
You should be able like to go to next page. I don't know.
Yeah, that's why I don't know how to do that. But so I need to clean it every time. Okay. Sorry. Okay, so again, let's use this. So F is a
from P to P, yes.
From P to P. So the corresponding bisection sigma F is a map from M to omega. Okay.
Yes.
So how we define sigma f? So so assume U belong to a fiber over X, where X is an element in M. Then we
So
have,
maybe you should call it M.
Okay. Okay, but okay. You prefer M, okay? So then we call it M. Okay. Then sigma f of M, okay, is equal to equivalent class because it's a number, where the second factor is U and the first factor and F of U. And this is you can see that the composition of sigma f with S is just equal to identities, and the composition of sigma and T is a diffeomorphism because it is a bundle map, and this is the case.
And F sigma, what is F sigma now?
Okay, so F sigma. So assume F sigma is a map from M to omega. Okay, so now let's define F of sigma of P. Okay, assume sigma of X is equal to U, comma V. Here U should belong to the fiber over X. Okay, then we need to So then we need to define F sigma of U equal to V. This is just the definition. The correspondence between F and sigma in the classical case.
And V is, of course, also in the same fiber as U.
No, V is not necessarily in the same fiber. They could belong to a different fiber. Because
when I don't understand, how do you get? Yes, I see. Because you can permute the fibers. Okay, I've got you. Okay, okay.
And it doesn't. It doesn't preserve the fiber because
you have this identity condition only in one place, and on the other place it's just automorphism. Okay, okay.
Exactly.
Yeah, I've got you. No, this is brilliant. That's what I wanted to see. Thank you so much.
Yeah. This is a classical picture of the correspondence between the gauge group and the biagonal point.
Yeah.
Okay. So
perfect. Thank you.
So now let's come to the quantum case. So for a given gauge transformation, we can define the corresponding sigma f, which is given by 2.24. That is sigma f of A tensor A tilde equal to FA times A tilde. And this is well defined since we first need to show f of A tilde belongs to the co-invariant subalgebra. So we can see the first step is just a definition, and the second step we use the coaction to be an algebra map, and the third step we need to use F is a H co-module map, and the last step we use the definition of X biagonal point, since the element of X biagonal point is co-invariant under diagonal coaction. So and then finally we get delta of this one is equal to this one tensor epsilon H, which implies F of A tilde belongs to the subalgebra of co-invariance. And conversely, given any bisection, we can also define the algebra map F sigma from A to A, given by 2.25. And we can also see this is well defined since A0 tensor A11 tensor A12 belong to C of A, comma H tensor A. And the calculation can be given explicitly, and this just given by direct computation. And we can also see this correspondence from the biagonal point from the bisection to a gauge group is bijective. So on one hand, we have sigma f sigma of A tensor A tilde is equal to F sigma A times A tilde. This is just the definition given here. And second step, we use again the relation 2.25. Then we get it's equal to sigma of A0 tensor A11 tensor times A12 A tilde. And finally, we use again the definition of X1 biagonal point. Here it's a little long. Okay, here 2.13. We can see whenever A12 contact A tilde, then it became 1. So as a consequence, we have the last equalities. So on the other hand, for any element A and any gauge transformation F, you have F sigma F of A is equal to this one by the correspondence and also equal to this one, also by the definition. And then we see that here we also need to use the property of the translation map. That is when H1 upper 1 meet H upper 2, then it became the epsilon H, and then we result in F of A. Okay. As a conclusion, if B belongs to a center, so we have the both group of bisection and a group of gauge transformation. Then there is a group isomorphism between the bisection and the gauge group, and this isomorphism also restricts to be an isomorphism between the vertical subgroup. Okay.
And can you point your finger to where exactly you use the centrality of B in A?
What do you mean? Where
did you use this assumption that B is central in A?
Okay, so I think here we need for example, if we want to get this composition of sigma being an algebra map, we always need to use B belong to a center in order to make this to be an algebra map. But I cannot remember the detailed calculation. And also, in order to get sigma inverse to be the algebra map, we also need to require B belong to a center.
Yeah, but I have slight logical objection to the way you reason. If sigma is an algebra map, and if it is invertible, then it must be an algebra map. I mean, this is an elementary algebraic statement. So if you already have sigma by assumption an algebra map, so if it is invertible, so of course it is an algebra map. So I suppose what you really mean is that in order for sigma, which is an algebra map by assumption, by construction, to be invertible, you need B being in the center.
Yeah. I think this is
what you mean.
Yeah, okay. This is what I mean. Yes, exactly. We need B belong to a center. Yes, in this sense, I think.
Yeah, it's a very nice proposition.
I thank you very much. Okay, so but usually we can see as the algebra map, there is too much restriction on the group of bisection and the group of gauge transformation. So when we asking when we define a new bisection and the gauge group without asking them to be an algebra homomorphism, and this was first introduced by Thomas Perkinski. And in this talk, we will name it extended gauge group and extended bisection, which mention the difference between the previous one and the new one. And in the new definition is for Hopf-Galois extension, extended gauge group consists of the linear map from A to A, such that F is a commodule unital map. Moreover, F restrict on B belong to automorphism, and F is also some sense of left B linear. And we can see here, we forgot B to be an algebra map. And similarly, there is also the vertical version with the restriction that F restricts on B equal to identity on B. Okay. And similarly, there is also extended version of bisection, which is a unital convolution invertible map, so which is automatically invertible. And it's again satisfy the composition of T with sigma equal to identity, and the composition of S is sigma belong to automorphism on B, and it is also right bilinear and left bilinear. And similarly, we have the proposition that the extended gauge group is isomorphic to the extended bisection under the condition that B belongs to the center. Okay.
Wait, so now we need the centrality to establish this isomorphism alpha hat?
Yes.
And you have no problem with these guys being groups without B being central?
No. If B is not in the center, we have the problem with the group structure.
Because you don't have the inverse element. Okay. Yeah. Okay. So if B is not central, then all you've got are just monoids. Yeah, semi-groups with a neutral element, but they are not necessarily invertible. Okay. Okay.
So now we will concentrate our special case on the Hopf-Galois extension. So instead of Hopf-Galois extension in this section, I will talk about the Galois object, which can be viewed as a quantization of the principal bundle over a single point. So the definition is for any H Hopf algebra, a Galois object is a Hopf-Galois extension whose subalgebra of co-invariant to be the ground field complex number. And we can see that for any Hopf-Galois object A, the corresponding X-man-Schoenroot bialgebroid is not only a bialgebroid, since B is just a complex number, but it's also a Hopf algebra with an antipole given by 2.26. And this formula was also given by a paper, by an article by Schoenroot in 2000. And but in general, the X-man-Schoenroot bialgebroid is not a Hopf algebroid, since we don't.
Yeah, but isn't it a Hopf algebroid or something like this?
Yeah, there is a concept of Hopf algebroid where we have the antipole on the bialgebroid, but that requires so much. There have several conditions on the antipoles, and there are even several different definitions of the Hopf bialgebroid.
Yeah, surely I know that these OID definitions are quite complicated in the quantum world, but they exist, and they even exist in the C-star setting, if I remember correctly. So I don't want anybody to be under the impression that when you go quantum, it's just a bialgebroid, right? Here the point is not that the bialgebroid becomes a Hopf algebra and all of a sudden miraculously the antipode appears. No, I mean you have the antipode also in full generality, except that it's in a messy setting of Hopf algebroids. But once your OID stuff is over the ground field, it just OID is gone, and your bialgebroid is a bialgebra, your Hopf algebroid is Hopf algebra, because your ground, the ring over which you take all your structures now the ground field.
Yeah, exactly. Yeah. Thanks for the comment. And it's also what I mentioned before, that this B ring and B core ring also become a algebra and a co-algebra in the case B is equal to a complex number. That is a similar story. Yes, exactly. Thanks for the comment. Okay, so in this case, the corresponding X-man bialgebroid of the Galois object is also the Hopf algebra by the given antipole in 2.26. And the most simple example is for any Hopf algebra, it is a Hopf-Galois. It is a Galois object of itself with a coaction given by the core product. And in this case, the Hopf algebra itself is isomorphic to the corresponding X-man bialgebroid C of A, H, wherein where the isomorphic map is given by 2.73, that is phi of H equal to H1 tensor S H2, and we can check H1 tensor S of H2 is a co-invariant on the diagonal action. Okay, and the next example is if H is a co-commutative Hopf algebra and A be a Galois object, then the bialgebroid is isomorphic to H as a Hopf algebra via the translation map. So as a consequence, we have the gauge group isomorphic to a group of bisection, and it's also isomorphic to the group of character on H. And also there is the same story on the extended version of extended gauge group and extended bisection and extended character, where the extended character means a group of convolution invertible unit map from H to C. Okay. So next, I will give a special example of the co-commutative Hopf algebra. But
do you realize you have only 6 minutes left?
Oh, okay, only 6 minutes.
Yes.
Okay, so I saw I can end at 7 o'clock. Okay, so I need to be hurried. So maybe I will skip this example, but instead I will talk about the Taft algebra. So a Taft algebra is a non-commutative and non-co-commutative algebra generated by X and G, subject to the relation Xg equal to Qgx, and there is also a co-commutative core product given here. And
well, it's not co-commutative. Wait.
No, it's not common. It's not co-commutative. It's neither commutative nor co-commutative because dirt of A is equal to 1 tensor X plus X tensor G. Okay. And for any Galois object of this type algebra is generated by capital X and G, where they have the commutation relation exactly similar like the one as the type algebra, but instead we have X, capital X to N equal to S, and the coaction is also given similarly as the core product, but here we just need to replace the small x by capital X and small g by capital G.
Taft algebra is a Hopf algebra, is that correct?
I beg your pardon, sorry?
Is the Taft algebra a Hopf algebra?
Yes, it is a Hopf algebra, and its antipole and the core unit and core product are all defined here. Okay.
And you have one Taft algebra for each n, for each capital N?
Yes.
How many Taft algebras?
So for each n, the integer, there is a Taft algebra. So we have different kind of algebra depends on how much dimension you used. If this n is 3, then we have a 9-dimensional Taft algebra. If this n is 2, we have 4-dimensional Taft algebra. And this algebra is also.
You are writing it as T sub n.
Yes.
You mean for each integer n equal to bigger than 2, you have one Taft algebra?
Yes.
Is that correct?
Yes. For each n larger than 2, there is a Taft algebra.
So I understand that it doesn't matter which primitive nth root of unity you choose. It will be an isomorphic Hopf algebra.
It doesn't matter which primitive nth root you choose.
Right?
Hopf algebra. This is a finite dimensional Hopf algebra.
Yeah, n squared.
Yeah, this is time-dimensional. Yes, exactly. It's an n squared dimensional.
It's not commutative and it's not co-commutative.
Yep. Exactly.
Yeah, exactly. Oh, you say here on your slide, you say it is a Hopf algebra with co-product. Yeah, okay, good.
Yeah, this is a Hopf algebra, which is neither commutative nor
very good.
Yeah,
okay, good.
I'm sorry, I'm a bit in hurry since I only have 6 minutes.
Well, now we have 3 minutes.
Okay, sorry. 3 minutes, sorry.
Yeah, okay. 3 minutes. 3 minutes.
Okay.
3 minutes for 11 slides.
Okay. And so we have this Galois objects of the type algebra. Since the canonical map is bijective and the co-invariant subalgebra is just the complex number. Okay, and we can also show that the corresponding exponent by Algebra is isomorphic to type algebra itself, and this resulting in the that the gauge group and the bisection is isomorphic to that n. And if we represent them, but for the extended gauge group, the situation will be much complex. And in this case, for n equal to 3, we can represent the gauge element, gauge transformation as a 9x9 matrix. And this matrix is a blockwise diagonalized. And on the diagonal element, they have some tricky conditions. That if in the first block, we have 1, alpha 2, alpha 1. And the second block, we have alpha 2, alpha 1, 1. And third block, we have alpha 1, 1, alpha 2. Okay, now I will construct a cross module in terms of the group of bisection and group of automorphism. First, recall that the cross module consists of the data of 2 groups and the 2 group morphisms from M to N and from N to automorphism M, such that they satisfy the Pfeffer condition. And in the story of bialgebrite, we first define the automorphism of bialgebrite is a pair of algebra map, and where the capital phi from L to L is the algebra automorphism, and small phi is also algebra automorphism.
Okay.
Okay. Some question?
Okay, very good. So you have generalized some classical facts.
Yeah.
To the non-commutative case. Okay, yeah. Very good. Good.
So could I continue, or you want me to stop here? Because this.
No. You can continue, but Paul said he has to go, so he's sort of.
Yeah.
Oh, sorry. Because if you want, it's only 1 minute, so.
No, go ahead. Only 1 minute, but go ahead.
Okay, probably I will spend another 5 minutes to finish.
Yeah.
Okay. So first, automorphism consists of two pairs of algebra automorphism. The first is one is from L to L, and second one is from B to B. They satisfy some compatibility conditions 1, 2, 3, 4, where 3 and 4 means phi is a core-ring map on the corresponding core-ring structure of L. So as across the module, we need to define the map from one group to another, where at map is a map from the group of bisections to a group of automorphism, which is given by 2.33, that at phi of A tensor A tilde equal to F sigma A tensor F sigma A tilde. And the action of the automorphism on the bisection is equal to the composition of phi and sigma and the small phi inverse. So the the Pfeffer condition can also be checked satisfied in the sense of this and this. Okay, so again, if B belongs to the center of the total space, then the data of group bisection and the group of automorphism is across the module. Okay, so there is also a similar story on the extended automorphism and extended bisection. Here, the extended automorphism again need to require two pair of map, and here phi is still an algebra automorphism, but capital phi is only a unit or invertible map from L to L, which satisfies the 1, 2, 3, 4 condition as given above. And here again we have the at map from which maps the extended bisection to the extended automorphism. And also there is a corresponding action of the automorphism on the bisection. And we have similarly have a extended version of the crossed module. And at last, I will go back again on the Galois object A of any Hopf algebra. And in this case, the bisection is coming to be a character on the corresponding bialgebra. And as using the formula above, we can calculate at phi of C is equal to phi of C1, C2 times phi of S33. And for the
but wait. I mean, here when you say the corresponding bialgebroid A, this bialgebroid A is actually a Hopf algebra.
I'm sorry, my signal is not so good. Could you repeat again?
You say let CAH, A comma H be the corresponding bialgebroid of A. So this is just a Hopf algebra, right?
Yeah, this is just a Hopf algebra. Yeah, that's why we have the bisection equal to the characters. Because the base space is just a complex number. That's why the bisection is algebra map. So from C to B, and B is a complex number. That's why it is just the character on C of A. So then we can compute at phi of C equal to phi of C1 times C2 times phi of SC3. And for the extended version, we have something similar, but instead of phi of SC3, we have phi inverse of C3. And an example for the top algebra with this Galois object. So we can check any. So the group of bisection and the group of character is equal to the Chiclet group, where for any generic character phi r from Tn to C, we can result it on the generator X and G by phi r of L equal to 0 and phi r of G equal to R, where R is the nth root of unities. Then we can compute with the help of 2.41 the corresponding automorphism at phi r of G equal to G and at phi r of L equal to R inverse X. And we can see AD map is injective. And we can also, it is also known by Schoenbrook that the automorphism of the Hopf algebra automorphism on top algebra is a non-zero complex number. And since one can define any automorphism Fr on X equal to Rx and Fr of G equal to G, and compare with this result on the generator, we can see at phi r is equal to Fr inverse. And one can also check the action of the automorphism on the bisection is trivial. So some question? Okay, no, nothing. Okay, so we can also see the action of F on phi is trivial, since at is a injective map, and the result on the generator is the same. And then across the module, the action of automorphism on the characters is trivial. And this is the data consists of the bisection, and automorphism is isomorphic to the non-zero complex number, and that n with the inclusion map I, where I is given by I of r equal to e to the minus I to pi r over n, and C star acting trivially on that n. And finally, on the extended version of the automorphism, it's just extended on T2, and which can be represented by its basis for matrix is given by 2.45 with a diagonal element A1, A2 being non-zero, and one can also check for any given extended bisection. One can also calculate the representation of at phi by again for matrix. But here we can see this matrix is the set of this matrix is a subset of this matrix, since here we need to require A2 is equal to the inverse of A1. And we can see the at map is an injective map. But in the extended sense, we have the action of the automorphism on the bisection non-trivial, since the representation of the action under the at map is different with the one given in 2.46. And we conclude that this given cross the module is a not trivial cross the module. Thank you very much. And this is all for my talk.
Yeah, thank you very much. I'm showing the picture of clapping hands. Thank you so much. And let's open the question session. Any questions, please?
I would have one question and one comment.
Okay.
So they are in bijection. Okay.
Okay. So first, the question. In your first deformation, in the example, your base was a theta deformation.
Yes, the base is theta deformation, yes.
What about the total space? Is it some special kind of deformation?
Yeah, the total space is a S2 deformation. I mean, because the total space algebra satisfies the commutation relation up to R matrix, and this special R matrix is controlled by 3 parameters U0 and U1 and U2, and they are restricted under where U0 square plus U1 square plus U2 square U21. That means the total space algebra is in some sense S2 deformation.
So for what? How do you compute out of a point on S2? How do you a triple of real numbers on the sphere? How do you compute theta?
You mean on S2 there is no theta. You mean on the base space, right?
No. I mean
the total space.
I understand it. If I understand you correctly, your S7 is deformed by parameters coming from the sphere S2.
Yeah, exactly.
Yeah. So and when you say that the base space sphere S4 theta is controlled just by one parameter theta. So,
yeah, exactly.
So how do you relate the parameters deforming S7 with the parameters deforming S4?
Okay. So you can see here. So we have here the commutation relation on the base space, where we after diagonalize this matrix of y and y star, we can see E of I theta is just the eigenvalue of this matrix, and this matrix consists of the entrance in terms of U0, U1, and U2. That is the case, and how they related.
Perfect.
Yeah.
But I remember that there was also a paper of Joe Varilli about S7 theta as a fibration over S4 theta with SU2 action. So it must be a special case of what you are doing.
Yeah, exactly. That is a special case. So if we kill U2, that is makes U2 equal to 0. So there is U0 square plus U1 square U21. So this is exactly the theta deformation also on the total space. So here we just add another parameter U2 in this case.
Okay, so how do you get this theta on S7 out of use? How say it again? Can you write it maybe?
Yeah, I mean here you have one parameter U0 stay the same on another parameter. Probably there is a this U0 is just a cosine theta, and here we have I of sine
I've
theta,
got you. Okay.
and then is a U1. That is the case, but we don't need
Okay.
to have the matrix one.
So you will have a complex number U0 plus I U1, and this will be your complex number, and this is how you get your theta.
Yes.
But you have this additional degree of freedom given by U2. This is very nice.
Yeah, exactly.
Okay, so is it related to the fact that quaternions, which are square roots of -1, minus identity, form a two-dimensional sphere?
You mean square root equal to 1?
Yes, there is a two-dimensional sphere of quaternions whose square is equal to minus identity.
Okay, why this square is equal to minus identity? You mean so the basic quaternion is square equal to minus identity, but I don't understand why the quaternion have a sphere dimensional 2.
No. So this is a two-dimensional sphere of imaginary units. Okay. So I wonder how all these complicated expressions can be explained in terms of the geometry of quaternions and embeddings of complex numbers into quaternions. So
okay. So I think the embedding of complex number into quaternion is
it's a two-dimensional sphere.
Yeah, it is a two-dimensional sphere, but that is another story probably. I didn't understand what you mean. Or you want to talk about the lower dimensional Hopf vibration from S3 to S2 with the fiber S1. You want to talk about that?
Yes. So what is interesting here that you are talking about the deformation of the instanton bundle.
Yes.
It's one of these famous Hopf vibrations.
Yes, exactly.
And on the level of this parameter of deformations, you also obtain Hopf vibrations.
Yeah.
So these are Hopf vibrations deformed along Hopf vibrations in a sense.
Yes.
Geometrical.
It seems to be, but it seems to be this Hopf vibration is just on the parameters, and the Hopf vibration we are talking about is about the real Hopf vibration. Yeah,
very nice.
And this is just on the parameter on the deformation. Exactly.
Yes.
You're right.
This is paradoxical.
Okay.
Yeah. So I have a question. Not a question now. A comment about centrality of this base algebra in this total algebra. So in many places, the structures defined for this Ehresmann-Scheinberg groupoid depend on the translation map.
Yeah, exactly.
And the centrality of the base algebra, total algebra, is tantamount to the fact, maybe not tantamount, it's needed to prove that the translation map is an algebra map from the Hopf algebra to the enveloping algebra of the form A op over tensor over B with A.
Okay. Yeah.
So this effect explains the role of this.
Very good point, Tomek. Yes, very good.
Yeah. This is very
of this.
I mean this point is also given by the paper of Gianni and Chiaha and Paolo, and there they show when this Hopf algebra is quasi commutative and also under some quasi condition I cannot remember. Then we need to also require this base space algebra to belong to the center. And in this case, we have a corresponding translation map being the algebra map. Exactly.
Yes, precisely. Yes.
So Tomek answered my question, which I was asking during the talk. Where do you actually use this centrality? You use it to have
Yes.
tau being an algebra. Now it's clear.
Yes, you're welcome.
Thank you very much.
Okay. Can I ask?
Go ahead, Ludwig.
Ludwig? Yes, so one actually is I would like to ask Gianni because he told me that about completions, C-star algebra completions. I think there is a recent paper by Wojtek Szymański and postdoc when there's some problem with one of the generators which has to be killed in this symplectic seven sphere of Gianni and Chiara Pagani some time ago. Maybe Gianni can comment on that if he is around still.
I don't know. He definitely was around.
So apparently there's some recent preprint, I think, on the archive by Wojtek, which I did not see yet, but
no, Gianni's gone.
Okay, there may be some complications about C-star. I mean, one has to be careful with C-star completions. Should be studied separately, all that stuff, okay?
Okay, very good.
Second thing is, maybe Piotr remember in our paper about braided stuff.
Yes.
We had some problems with star. So my question is about star Hopf and star Hopf-Galois objects. If XIAO, if you discuss it also, that stuff, star structure on your Hopf-Galois object?
No, at the moment we didn't study the star structure on the Hopf-Galois extension because probably there's some complicated stuff there, but probably we can work it later.
Okay.
By the way, Ludwig, since you mentioned this Galois object problem, I have some baby questions here. So first, what is this AS Galois object over the Taft algebra? Can you tell me more precisely what it is?
Could you repeat the question? I didn't hear clearly.
AS, you studied Galois object over Taft algebras.
Yes.
And I want to know more precisely what they are. I mean, in particular, they are not Hopf algebras, are they?
You mean the X-man algebra? They are the Hopf algebra. I mean, because
can you show this slide again? You have some slides.
Show the slide.
Yeah, yes. Sure. Let me show the slide again.
For the Taft.
Yes.
Okay, so this is Taft algebra.
Yeah, we know it. Yes.
And then there is a isomorphic map between the Taft algebra and is X-man algebra. And on the generators, we can have the correspondence.
Yeah, but this is the Hopf algebra of Eresman-Schauenburg. I'm asking. This is not surprising. I think this is more generally true, not just for Taft algebras. But I'm asking, what is a Galois object? Yeah.
You mean the general issue on the Galois object? Yeah, I mean, this is
no, I'm asking what is a Galois object of a Taft algebra? You can classify Galois objects for a given Hopf algebra.
Okay. So, I mean, the Galois objects of any the Galois object of any Hopf algebra, right?
No, of Taft algebra.
Of Taft algebra. Okay, so it can be determined
by.
What
is AS?
Yeah, what is AS? Yes.
Okay, sorry. I always misunderstood. Okay, so AS is an algebra which can be determined by a single complex number, and they are so for each S they have an isomorphic class of the AS satisfy this commutation relation that x to n equal to s and g to n equal to 1 and so on. And this is a corresponding Galois object.
So XIAO, you claim that there is only one parameter complex number which classifies this.
Yes, it's only one parameter.
Okay.
Yes.
Yeah, actually, you had it in your slides, but then you sort of were too fast for me and I missed it. Okay, and in particular, do you have a claim that this algebra is not a Hopf algebra? It's not isomorphic with Taft algebra itself?
I think I only did explain this.
No, that's obvious. That's obvious. It always happens.
Yes,
this proposition
yes.
is irrelevant.
But then I don't do anything else.
Because you see, this is a very important question. You can give a fancy definition of a Galois object, but it often happens that your Galois object is just isomorphic, but in a fancy way, to your Hopf algebra. So this is an important question, and a question we had when studying Greenfield doubles. So
okay.
For modular pairs involution, for Hopf cyclic homology coefficients, this was a very important question, because it turned out that if you have this one-dimensional space of coefficients, then you are really talking about, on one hand side, Jeter-Greenfield modules are modules over the Greenfield double, and our anti-Greenfield modules turned out to be modules over a Galois object over the Greenfield double. However, you can prove that if there exists a modular pair involution, then in fact this Galois object is necessarily isomorphic to the Greenfield double. So it is itself a Hopf algebra. It's just a fancy different way of writing Hopf algebra. Okay. So this was a very important open problem for a long time. Is it true that every finite dimensional Hopf algebra admits modular pair involution? And luckily, the answer was no. Somebody did a PhD in Dresden on it, and this was a tough problem which we couldn't solve for quite a long time. And he provided us with a counterexample, which is good news, which means that there are Galois objects in this setting which are non-trivial, which are not Hopf algebras.
I see.
Because otherwise, if it would be just a change of notation, this is not so interesting. And yet at Greenfield, anti-Greenfield, the Greenfield double, anti-Greenfield double, that's the same thing as isomorphic. But we can see that is not always the case, because there are Hopf algebras, finite dimensional, in which the Galois object over the Greenfield double of this Hopf algebra, our anti-Greenfield double, is not a Hopf algebra. So this is why I'm asking such a question. But these are difficult questions in general, right? It's like a no-go theorem. We have to prove it, but it does not exist in isomorphism with some problem.
I see.
I was wondering about this Galois object, about the Taft algebra. If you really have a solid claim that this is not isomorphic to the Taft algebra itself as a Hopf algebra, unless, I don't know, S is equal to something, right? So, but you didn't.
I think if S is non-zero, then the Galois object itself is not isomorphic to the Taft algebra.
Yeah, then that's perfect. That's perfect. What I wanted to see.
I think this is not. I'm wondering, you are asking the Biagonal point. So if you're asking the Galois object itself, then it's not isomorphic as the Hopf algebra. Even as algebra, they are not isomorphic because they have.
Perfect.
They have a relation.
Yes.
Yeah, then because they have the relation x to n equal to s.
Yeah.
So that's why on the generator we kill every possibilities.
Okay, this is very good. This is very good, because the other proposition, this is always true. I mean, the Ehresmann-Scharenburg. Wait a second. No, wait a second. I'm wrong. Sorry, I'm wrong. This is look at this proposition. This is what happens here. This is a Scharenburg transform. So what Scharenburg did in this paper, where he introduced his quantum groupoid, basically said, all right, let's take a Galois object with its structural Hopf algebra. Let's construct this Ehresmann-Scharenburg quantum groupoid, which is just a Hopf algebra in this case. And in general, that's just another Hopf algebra which coacts on a Galois object on the other side. This left coaction commutes with the right coaction, and this Galois object from right becomes left Galois object, and because these two coactions commute, you can call it a bi-Galois object. And this is what Scharenburg did.
Yeah, this is Scharenburg done. Yeah.
So this is this very beautiful transformation, right? This is flipping over your right coaction into your left coaction over your Galois object, gives you another Hopf algebra. And it is a result, right? It is a result that it is isomorphic to the initial algebra. So it's like a conjugation, right? This is Scharenburg conjugation of Hopf algebra.
That's also
it's involutive because it's an involution, because when you apply it the second time, So when you now do the Scheinberg construction for the left Galois object for the CAT, then you'll go back to the initial Hopf algebra. That's known. This is like a star operation. It's idempotent, right? Not idempotent.
No.
Not idempotent.
Involution.
Anyway, a composition is identity with itself.
It's called unipotent.
Unipotent. Sorry, this is
Involution.
what I was looking for. Thank you. Yeah, and when you look in the particular case of studying these Galois objects over dreamful doubles, then we have a similar result with Ludwig and Elmar. That flipping over will give you an isomorphic Hopf algebra, right, Ludwig? Do I remember correctly?
I think so. Yes. Yes.
Yeah. Okay. But for us, what was highly non-trivial because of the definition. Our definition, we just changed things a little bit, and it was not clear whether our Galois object is not really just isomorphic to our dreamful double Hopf algebra. And it is if and only if there is a modular pairing involution. You can write explicit isomorphisms using a modular pairing involution. So there was a question, does there always exist a modular pairing involution? And luckily, this is not the case. We have some nice Hopf algebras where modular pairing involution do not exist. So our theory developed based on Galois objects is non-vacuous. Okay, I have, are there any further questions? If not, I have just one last question. Please, what are examples? What are good, nice, sexy examples of B central in A? What are nice quantum vibrations where the base is central in the total space?
Okay, an example, I think the Galois object is, of course, one of the example.
No, forget the Galois object. Yeah, that's obvious, of course. Galois object is obvious.
Yes, of course. I mean, it's obvious. That's, I will think about another.
Of course, you can do cross products, but that's also a cheap answer. We did with Ludwig SLQ2 at roots of unity, and then you had SL2C inside. Yes, that's also fine. But it's a cross product. I would like to have something genuinely a non-trivial quantum principal bundle, okay, where the base is commutative. And not only commutative, sorry, you need more. I mean, it's central. And commutativity is known. For instance, if you take this Matsumoto free sphere, right, which is like the equator in your sphere, which you just showed to us. Then if you take the U1 action on this theta sphere, the fixed points give you a classical sphere. But I'm not sure it's central.
Yeah,
I don't remember. Ludwig, do you remember whether the S2 in or Elmar, if Elmar is still around? I don't remember whether this S2 and S3 theta. Well, when you look at algebras, of course, it's central.
Don't remember. Yeah, it's nice to check. Yeah.
Because it's a very crucial assumption for you, and I'd like to see that the family of examples is rich enough to warrant development of the theory. And except for cheap answers like cross products and Galois objects, I don't see offhand so many candidates. It would be nice if you would give a class of examples, interesting non-trivial examples.
Maybe not now, but maybe in Warsaw during your stay.
Yeah, he's already in Warsaw, as I'm asking. Anyway, you don't know, but this is a question to ask, and we can begin by checking with this Matsumoto sphere over S2, right? You have a theta sphere, but a free sphere, and inside, as invariant subalgebra, you have just the commutative sphere subalgebra.
Okay, so the base space is S2, right?
Yes, S2.
But is it
the structure is U1. The sphere is like a Hopf vibration. But the only thing that is twisted is S3.
Okay, but the base space S2 is a commutative?
Yes, it's commutative, but I don't know if it's central.
Ah, okay, I see.
This I don't remember.
Okay, I will check this sphere. I will check.
It might be because basically this Matsumoto sphere is given by two generators, and they satisfy the sphere equation WW star plus ZZ star is equal to 1, and that W and Z are theta commutative. Okay, for a change they are normal operators, so they commute with their adjoints.
Okay,
but W and Z are theta commutative. So then I believe that when you look at coaction invariant subalgebra, you'll have combinations of the sort, I don't know, WZ star, WW star, and all that stuff.
I see. Okay, I'm afraid in this case, the base space should not belong to the center. So there is a coordinate called ZW star, and this cannot commute with, for example, that, because that commute with itself, but then we passing
through you're right.
And the W,
exactly.
Are the
yes, I agree with you. Yes, I agree with you. So yes, so you need to try harder. Yes. I agree with you. I think this is not central. Yes.
This is not a center.
I think this is not central. Right. Yeah. Beautiful. Yes. But then I want you. It's your job to give me beautiful examples of.
Yeah, I will think about it. Hopefully in a few days.
Okay, I'll go on hunger strike, and I will not eat until you give me a good example.
Okay.
So, do you understand, Xiao, that you are on quarantine in Warsaw, or
yeah?
Not really?
Tomorrow I will finish, and I can.
Okay, so you have only 24 hours to find nice examples.
Okay, great.
Yeah, and we meet tomorrow at IMPAN. By the way, so thank you one more time for a very interesting talk. And now, since winter is coming, we will now play the game of theorems in a way that involves ski. And we involve ski in the sense that our next speaker is Wojtek Szymański. And then in January, our first speaker is Tomek Brzeziński. So we will have 2 ski talks.
Provided I will not be skiing.
Yes, because then Tomek goes to ski, really. And so 16th of December, the last talk before Christmas is by Wojtek Szymański. And then the first talk after Christmas, which I believe is 13th of January, it's Tomek Brzeziński on his joint work with Wojtek Szymański. But I'm afraid Wojtek Szymański might not speak about the joint work with Tomek Brzeziński. I don't know. He has a student.
I hope so.
I hope so, yes.
Otherwise, I will have to change the topic.
Exactly. But we will know the abstract soon. And I guess thank you very much again. And we will see each other next week. Okay. Bye-bye. All the best. I stop recording.
Thank you.